Good morning, everyone. In the last class, we discussed about transistor operation, and in today's class, we discussed about common base input output, common emitter input output characteristics, and also current relations. Clear? Coming to the transistor operating modes, here three modes of operation in the transistor are possible. First one is active mode, in which base emitter junction is forward and base collector junction is reverse bias. If you remember the transistor operation, we are having two sides, input side as well as output side. If the input side is forward bias and output side is reverse bias, then that is called active mode. Coming to the saturation mode, one more mode possible is saturation mode. If the base to emitter junction is forward bias and base to collector junction is forward bias, that means both junctions are both side input output both are forward bias, then it is called saturation mode. Coming to the cutoff, the name indicates the name is clearly representing it is cutoff mode. That means both sides are reverse bias. Clear? Those are the modes which are possible in transistor operation mode. Transistor operation. These are the three configurations available in the transistor. Here having three terminals. If we make each and every terminal common, then there results three configurations which are common base, common emitter, common collector. In the common base connection, the common base terminology is derived from the fact base is common to both input and output sides of the configuration. That results common base. Base is acting common between input as well as output like this. Base is common. Input side is emitter to base is called input side. Collector to base is called output side, in which base is common. If you're having three friends, if one of the friend is common to your two members, if one friend is common to two members, then you can call it as common friend. In the same way, if base is common to input side as well as output side, then that is called common base. This is the common base NPN configuration. This is the common base PNP configuration. Clear? Next, we will move to the, that is the current amplification factor. Current amplification factor alpha is nothing but the ratio of change in collector current to the change in emitter current at constant VCB is known as current amplification factor alpha. Alpha equal to change in output current divided by change in input current. Practically, the current gain of the common base configuration is range is 1. We will discuss later why it is 1. Okay. Now coming to the expression for collector current. In the previous class, we discussed emitter current is IC plus IB. You all know that. Because the charge carriers, some are distributed to base and remaining total rest of the charge carriers will move to the collector. So that's why emitter current is equal to IC plus IB. We will explore that emitter current now. Here, the output current IC is due to the, in the active mode, input is forward bias and output is reverse bias. If you consider IC collector current, here whatever the current you are getting, that is IE with the fraction of alpha, it is due to the forward biasing of the input side, and the rest of the current ICBO is nothing but leakage current, which is due to the reverse bias on the output side. In the active mode, input side is forward bias, output side is reverse bias. Due to the forward bias, there will be a current which is called as alpha E. Due to the reverse bias, there will be a current flow which is called ICBO, and it is also called leakage current, which results in reverse bias due to the minority charge carriers. Clear? So like that, I mentioned in the 2 points. First point is due to the minority charge carriers, there will be a current results that is called ICBO. Due to the forward bias, there will be current results alpha I, where alpha is denotes as current amplification factor. Clear? Coming to the configuration in detail. This is the common base, common emitter, common collector. Simply, I can consider as in the common base is the middle. Whatever the common terminal, please kept it at middle. This is base, kept it middle. Here emitter, kept at middle. Here collector, kept at middle. Clear? If base is kept middle, then emitter will come input side, collector will be on the output side. Here what is the input terminal? E. So simply input current is IE. Here what is the output terminal? C. So output current is IC. here in the same way, input voltage is VEB. Now coming to the common emitter, input terminal is B, output terminal is C. So output current is IC, output voltage is VCE. Okay, in the common emitter, input terminal is base. So that's why input current is IB. Here I gave the example for the output current, what is output current and what is output voltage. Because to get the clarity, output terminal is C collector. So that's why output current is IC. Output is connected between collector to emitter. So please consider the voltage as VCE. When you are taking the voltage, you have to mention two terminals. When you are taking the current, please mention one terminal. While coming to the common collector, it is also same as common emitter. Please swap these terminals. Okay, swap these terminals. Please kept this collector as common and emitter to the output side. Then input current IB, input voltage VCB. Like this, you can get idea. Yes, coming to the input characteristics. What is meant by input characteristic? If you consider the transistor, input characteristics are nothing but if you see this figure, what is the input terminal? Emitter. Okay. When you are doing input characteristics, you have to know if you are varying this input voltage, what is the effect of the current on input side. That means input characteristics are nothing but if vary the input voltage and consider what is the effect of the input current, how it is affected if I am varying the input voltage. That is nothing but input characteristics. Okay. And when you are calculating this input characteristics, please kept output voltage as constant. What is the technical reason for that? If I am varying at a time input voltage and output voltage, clear, if I am varying at a time input voltage and output voltage, how can I know? How can I know the effect of the input voltage on input current? So that's why please kept output voltage as constant when you are plotting the input characteristics. So input characteristics are nothing but between input current and input voltage, whereas the condition is kept output voltage as constant. Okay. So I am assuming, please assume uh, output voltage is 1 volt. Okay, output voltage is 1 volt. Now what are the terminals on the input side? Emitter, base. Please connect forward bias to this input side to draw the input characteristics. Here I am considering only input side because these are the input characteristics. Make this forward bias. How can you make this forward bias? Connect negative to the emitter, positive to the p-type. Then it will be forward bias. Okay. I'm assuming here I also mentioned, sorry, 5 volts, VCB equal to 5 volts. Then I am increasing the input voltage. Here if I increase the input voltage, it is same as diode. That means N is connected to negative, P is connected to positive. That means it is looking like diode forward bias. So if it is looking like diode forward bias, please remember the, if you recall the diode forward bias VI characteristics, after reaching the cut-in voltage, automatically the current will be rises. Here I mentioned what is the output voltage, VCB equal to 5 volts. Please kept it constant and vary the input voltage. Calculate the input current, which is IE. IE is in milliamperes. In the forward bias, the input current is in milliamperes. That means input characteristics are all look like some PN diode input characteristics, PN diode forward bias characteristics. Clear? Now we will see what is early effect. Early effect is comes into picture. Why we want to discuss early effect? Early effect why we want to discuss is, here I kept VCB equal to 5 volts. Here I kept VCB equal to 5 volts, which is on output side. If I increase this VCB to the next value, if I increase this VCB to the next value, then is there any effect of that reverse bias voltage on input side? That thing I want to know. I am repeating, if I increase the voltage on output side, which is reverse bias, is there any effect on input current or else input side? Okay, that thing we have to discuss. And if you understand the concept of early effect, that things will be clear to you. What is the concept of early effect? First, I will say, if VCB increases to VCB equal to 10 volts, that means in the previous case VCB is 5 volts. Now it is incremented to 10 volts. If VCB increases, if you remember in the diode reverse bias voltage increases, obviously depletion layer width increases. Clear? Reverse bias voltage increases, obviously depletion layer width increases. Now, if the reverse bias voltage increases, depletion layer width increases, but it penetrates more deeper into base side. Okay, but it penetrates more deeper into base side. Why it penetrate more deeper into base side? I'll clarify. Emitter, base, collector. This is the construction of the transistor. In this, you know that base is, what is the doping order of the base? Lightly doped. If base is lightly doped, from the doping concentration formula, you know that depletion layer width, width of the depletion layer is inversely proportional to the doping concentration. Clear? If the doping concentration is low, then the width of the depletion layer is high. Here the doping concentration of the base, is obviously low. When the doping concentration of the base is low, then width of the depletion layer on the base side is increased. So that's why the depletion layer will penetrate more towards to the base. The depletion layer will penetrate more towards to the base. Okay, I'll show the picture for that like this. Here, the depletion, this is the normal case for low VAF. This is the first case. This is the depletion layer width. When I increase the reverse bias voltage on output side, now the depletion layer will penetrate more towards the base because base is slightly doped. Okay, now what happened? If you compared with this diagram, here base width is more. That means base width is nothing but whatever the width remains without having depletion layer. Here the yellow dots are representing the actual base width without depletion layer. Here the yellow dots are very, very less. Now what happen if the actual base width is reduced? If the base is having more depletion region, what happen is, if the base width reduces, then automatically the electrons which are coming from here, the electrons cross this junction which is present from emitter to base. They cross from emitter to base. In the previous example, I told that here in the emitter 100 electrons are there, in the base 10 holes are there, in the collector how many electrons will come to the collector? 100 minus 10, sorry, equal to 90. Now here, if the base width reduces, the chance of recombination of the electrons with the holes are also reduces. Here there is no area to recombine with the holes present in the base. Area is reduces. Now that is nothing but, if area is not available, okay, if there is no free space available for the electrons to flow in the base, then obviously the electron will move towards the collector. That means in the previous case, if 90 electrons are available, now in this case 95 electrons are available for the conduction in the collector. So that's why, due to this effect is called early effect. Due to this, what happen is, IB current is reduced, IC current is increased. Here there is no free space to move the charge carriers. If there are no moment of charge carriers in the base, there is no current. That means small current will result here. Whatever the carriers are available in the emitter, those are crossed to the collector. That means large number of carriers are available in the collector for the conduction. That results collector current increase, base current decreases. That was the early effect. If you remember this point, it is very easy to understand the clearly I mentioned if ECB increases, base width decreases and IB decreases, IE increases. If you don't understand the early effect concept, you can write it as if reverse bias increase, base width decreases, then automatically if base width decrease, IB decrease. Like that you can imagine and you can remember. Okay, this was the concept of early effect. Now, if you see the input characteristics in the common base, okay, in the common base, what I said that IE increases. Okay. If the reverse bias voltage on output side is increases, due to that early effect will comes into picture and due to that IE current will increase. So that's why the curve moved to the left side. Here I clearly mentioned the curve shift to the left side to indicate IE is increases. Why I can say please consider the point here. Okay. And draw the lines here at this point. What is the current at this in this curve? Okay, in this curve, if I am assuming the current is suppose 2 milliamperes. Okay, now at this point, if we increase the line towards this curve, the current at this point is, what is the current at this point? It will be greater than 2 or not? Obviously it will be greater than 2. Suppose I am assuming 4. That means IE current is increases. Okay, if I increase the reverse bias voltage on the output side. Clear? While coming to the common base, okay, IE current is increases, curve moves to the left side. If you discuss the common emitter input characteristics, okay, please see here. Common emitter, what is the input terminal? Base. So that's why input current is IB. For which terminal you will apply the voltage? Base to emitter. So that's why input voltage is VEB. Clear all of you? Now, due to the early effect, IB decreases. I said that clearly. So here I mentioned the same thing. If you observe, if you increase the voltage on output side, okay, here 510 left side, here 510 right side. That means here IB current decreases, curve moves to right side. Here IE current increases, curve move to left side due to the early effect. If you understand the early effect, then you will get the clear picture of input characteristics in CE as well as CB. Now we will move to understand what are the output characteristics. To understand the output characteristics, you have to understand current relations first. In CB, CE, CC. Clearly, I can mention already output current IC in common base is equal to alpha into IE. Why this alpha comes into picture is, from the emitter, the total number of electrons are not getting in the collector. Some fraction may be reduced. That fraction is called as alpha, which is current amplification factor. The first current is due to the forward biasing of the input side. The second current is due to the reverse biasing of the output side. Now, this reverse biasing current is very, very negligible. It is due to minority charge current. So that's why I'm neglected while moving to the next equation. Okay, IC by IE. If I move this IE to the left hand side, IC by IE equal to alpha. IC, IE. In practically, IC, IE both are almost approximately equal. So that's why equal to 1. From this equation, I can get IC equal to IE. In practical, okay, in practical, IC approximately equal to IE. Okay, because we are having base is very, very lightly doped. So that's why minute current will flow in base. Whatever the carriers are available in emitter are mostly available or mostly crossed to the collector for the purpose of conduction. So in the common base, IC is approximately equal to IE. Here why I derived this relation is, if you see this common base, what is the output current? IC. What is the input current? IE. Okay, here I am deriving the relation between output current and input current. Why I am deriving the relation is the transistor is a current control device. Transistor is a current control device. If you remember the operation of the transistor, if suppose carriers are not there, if input current is not there, there is no output current present in the transistor. If there are no carriers available in the emitter, then obviously there are no carriers available in the collector. Transistor is a current control device in which output current depends on input current. So that's why we will see the characteristics of in output characteristics in common base, which are output characteristics are nothing but output current versus output voltage. And what is the condition is, please kept input current as constant, because technically what is the reason is, what are the output characteristics? Output current versus output voltage. Output current is IC, voltage is VCB. So please kept input current is constant. If you don't having any input current, if any input current is not there, there is no output current, because IC equal to IE. So that's why you have to maintain minimum input current at the transistor. Clear? These are the input characteristics in common base. Okay, here I kept IE equal to 1 milliampere. Now give 1 minute. Here this was the output voltage VCE. Vary this input voltage and calculate what is collector current. Clear? VCE is the reverse bias voltage, and calculate what is IC. If you increase VCE, it is reverse bias. Due to the reverse biasing of VCE, is there any current possible? No. But here there will be a current possible due to that IC is equal to IE. If IE equal to 1 milliampere, if IE equal to 1 milliampere, then from this relation I can set that IC is equal to IE. If IE equal to 1 milliampere, then IC is also 1 milliampere. In the starting stage, it will require some time to reach to 1. Then after that, constant 1 milliampere current is flow, because input current is 1 milliampere. Then at the collector side also 1 milliampere will flow. In the same way, if IE equal to 2 milliampere, IC is also 2 milliampere. If IE equal to 3, IC is also 3 milliamperes. Like this, you can draw the output characteristics in CV. I hope it will clear for all of you. Next, we will move to the output characteristics on common emitter. Clear? See the current relations in the common emitter. IC equal to alpha IE plus ICBO, same equation. I can directly write it as from the common base. Take out ICBO to the left side, IC minus ICBO equal to alpha IE. IC minus IC. IE is nothing but what you know from the transistor operation, IE equal to IB plus ICB. Okay, replace that. If you take out this alpha to the left hand side, you will get like this. Okay, now please divide alpha with the both parameters IC and ICBO. Okay, from this equation, common out the term IC, which is available on both sides. So like this, you will get, finally, you will get the current equation like this. Okay, that means here you will get IC equal to beta IB plus 1 plus beta into ICBO. How you will get? Alpha by 1 minus alpha equal to beta, 1 by 1 minus alpha equal to 1 plus beta. There are relations are available. Here I can give the clear relations. Okay, please go through this. Alpha equal to IC by IE. Alpha equal to IC by IE. Please replace this IE with IB plus IC. You will get like this. Okay, divide with IB. Numerator and denominator, please divide with IB. You will get alpha equal to beta by 1 plus beta. What is meant by beta? Beta is the current gain in the common emitter configuration. Clear? So what is the beta? Output current divided by input current. If you see this diagram, in the common emitter, output current is IC, input current is IB. So what is the current gain? Gain is nothing but output current divided by input current. Clear? Gain is nothing but output current divided by input current. Here I mentioned the same thing. IC by IB. Beta IB is nothing but from the current equation IE equal to IB plus IC, IB equal to IE minus IC. Divide this entire equation with IE. You will get like this. IC by IE is nothing but alpha. Please replace with alpha. IE by IE is nothing but 1. Both are cancelled. IC by IE equal to alpha. Now we will get beta equal to alpha by 1 minus alpha. So that's why I replaced alpha by 1 minus alpha with beta. Okay. Remaining 1 minus 1 by 1 minus alpha you also get from this relation. Please go through this. You will understand clearly. Okay, from this equation, you can get the clarity. IC equal to beta IB. That means output current IC is depends upon the input current and it is depends upon beta. Please go through this. IC equal to beta into IB plus 1 plus beta into IC2. This is the minute current. Please neglect this current and it is due to reverse bias of the output side. Okay, now you will get IC by IB equal to beta. Beta is nothing but current gain. Current gain, what is the units for IC? IC is in milliamperes. What are the units of IB? I clearly mentioned that base is lightly doped. So that's why IB is in the range of microamperes or nanoamperes. Okay. Milliamperes divided by microamperes. If you divide that, I'll give one example. 1 milliampere. If suppose I am assuming IC equal to 1 milliampere, IB equal to 1 microampere. Please convert microampere to milliampere. You will get 10 power minus 3. Okay. You will get 10 power minus 3. If you take out the 10 power minus 3 to the numerator, you will get 1 into 10 to the power of 3. That means what is the 10 to the power of 3 value? 10 to the power of 3 value is 1000. That means the current gain in the common emitter configuration is very, very high. Okay, very high. So in the common emitter configuration, the output characteristics are simply rising like this. Okay, rising like this. So that's why I have drawn like this. If IB equal to 1 microampere also, we will get the IC is in milliampere. Okay, because the output current collector current depends upon the input terminal current, which is emitter terminal. Output current is depends upon the charge carriers present in the emitter. So that's why we will get the output characteristics in the rising. Here if you observe, we will get straight lines. Here we won't get straight lines. We will get incrementing in all directions. That means like this. Okay, clear? Coming to the CC output characteristics, CC output characteristics are also same as CE. CC output characteristics are also same as CE. Same output characteristics you will get because in the CC output current is IE, input current is IB. IE by IB. IE is almost equal to IC in practical. So that's why output characteristics of CC is equal to CE. Clear all of you? I hope input characteristics, output characteristics are clear for all of you.